The next player in all of this, the people were just blown away by Einstein's wave-particle duality and Planck's quanta. They were kind of blown away by. Well, then, out of left field, more or less, came this guy named Niels Bohr. And Bohr is another one of the powerhouses of this section. And he came into this because he was trying to build a simple model of the atom. And he came about it because he was the first person to figure out possibly where sharp line spectra came from. And we're going to talk about what sharp line spectra are here in just a little bit. But needless to say, nobody had any idea where these sharp line spectra were coming from. And Bohr came along and came up with an idea that worked amazingly well, all things considered. He kind of pulled it out of left field, so it was a little bit different, but still, he did something that was really neat. He brought this field around. So let's talk about what sharp line spectra are, and then we can talk about what Bohr figured out. So this is light. This is like visible light. All right, it's coming in. And if you've ever sent it through a prism, or if you've seen that Pink Floyd album, anyway, just Dark Side of the Moon. Anyway, if you've ever seen light going through a prism, it makes a spectrum of colors. All right, so white light is actually all colors, basically. And the prism is able to separate it through refraction. And the blue light is usually, of course, as we talked about earlier, the shorter wavelengths, and the red light is usually the longer wavelengths, all right? And the refraction angle depends on the wavelength, and short wavelengths bend the most, so that's why blue is like way down here, all right? And the red actually doesn't bend very much, so that's what it is. But the important part here is that all white light really is a combination of colors, and you can separate them out with a prism, which is kind of cool. Let's try and figure out here which of the following forms of light will refract the least. All right. Now we've got red light, blue light, and black light. Now black light is not really appropriate here. Black light is a type of ultraviolet light that used to be really famous in the 70s. And if you're in a dark room with a black light, it makes your white things glow. It's a cool kind of psychedelic effect, but it's not really appropriate here. Now, short wavelengths will bend the most. All right. So we want to know what the shortest wavelength is. And you can see down there that blue is shorter than red, which is long. So this one's going to be red. It refracts the least, all right, relative to blue. Blue would do the most, red would do the least. And again, black light doesn't count here. So, cool.
If we pour methanol onto sodium chloride and ignite it, the flame produced is yellow in color. If instead of using sodium chloride we use boric acid, a compound made of boron, hydrogen, and oxygen, the flame produced is green in color. Each salt imparts a characteristic color. The emission of light by heated or burning objects provide important clues to our understanding of atoms.
Most of the time, you don't have pure white light, like you don't have all the colors. And a lot of the elements, if you put them and you, like they did in the video there, you can take like a salt of the element and put some methanol on it, which is just a way to get the flame going. And you'll see the different colors. So you can see down here in the lower right, like KCl and lead are kind of a darker kind of color. On the other hand, green can be boron. The red color can be things like strontium and stuff like that. All the elements have like a type of a color associated with them. And this process is exploited when it comes to neon lights. Neon lights, when they're excited, can have different colors to them. And the light bulbs themselves are usually filtered with some kind of a piece through it. The neon light itself has a certain color, and then they can put filters on it and stuff to see what happens. So this is kind of cool. If you have a pure element and you excite the atoms, you can actually get a specific color. You don't see white light because you don't have all the pieces. And again, this is the idea behind fireworks and all that kind of stuff.
If a high voltage is applied to an element in the gas phase, the element emits light. Using a prism, we can split the light into its component colors. Every element emits a distinct set of colors unique to that element.
people were really fascinated by the fact that some types of salts gave off certain colors, and they wanted to see what happens. So what they did is they created essentially like a type of a light bulb, and in the light bulb they had just that type of atom. They'd add some electricity to it, it excited the atoms, and then they placed it through a prism. And this is an example of hydrogen, what happens with hydrogen. Now the hydrogen bulb is kind of a red purple color kind of thing, and it looks pretty neat unto itself, but it's a lot different than the light bulbs we use in our house usually, which are kind of a white color and stuff. All right, but it's all right. Anyway, they took that red purplish kind of hydrogen light bulb, placed it through a prism, and lo and behold, they saw that there were 4 distinct sharp lines that came out of it. And you can see in that little picture, it's kind of like there were 2 kind of blue purple, one kind of in between, and then there was also a red one on the far side. The 397 nanometer is harder to see, but if you did see that, it would look kind of indigo or purple or whatever. But anyway, sharp line spectra are what you see when you take one of these light bulbs with the element in it and you place it through a prism. And these are super, super sharp lines, all right? So they're only one thing coming out. And they can measure the wavelengths of these things pretty accurately, so you can see the different values there for hydrogen. We're going to talk about hydrogen a lot in the next section here, so we'll see these numbers come up. Notice how they're nanometers, all right? So nanometers are usually visible lines. And it does depend on the element. So hydrogen is different than helium. Helium is different than lithium. Lithium is different from uranium, etc., etc. Here's a picture that shows, I think, a better representation of hydrogen. Again, the light bulb kind of thing is there on the left. They send it through what's called a double slit experiment, and that's just to give you a plane of light. You don't want to have other light sources come in and stuff like that. And then you place it through the prism, and instead of seeing that kind of reddish, purplish color of the light bulb, you see there the other lines, a red and a green and 2 purplish kind of lines, or 2 blue, depending on your video. And again, every element has this. So this can actually be used as a fingerprint to identify different elements, and that's really cool unto itself. The wavelengths are known to very high detail, and we're going to talk about these 4 right here. This one right here is harder to visibly see. If you have very sensitive eyes, then it's easier, but the 4 there that I kind of underlined are ones we're going to talk about a lot, and they're really cool. And again, those are used a lot of times to identify hydrogen. So if you had a mixture of gases, but you saw a line at 656.3 nanometers, probably then that line's going to be from hydrogen. As before, though, remember that wavelengths and frequencies and stuff like that have a relationship to energy. So you can see how the wavelengths are getting bigger as you go left to right. So longer wavelengths will have smaller frequencies and lower energies. On the other hand, if you go right to left, you can see that the energies are getting bigger because wavelengths are getting smaller, but the frequencies would be getting larger as well. Balmer was the first one to observe and measure those visible lines of hydrogen. So the Balmer series of hydrogen are basically the 4 lines starting at 410 and going over to 656.3 nanometers. Again, we'll talk about the 397 in a little bit too. Again, every element has its own fingerprint. So the top one up here on the left is hydrogen. Here's mercury. Notice how mercury has quite a few more lines than hydrogen, but again, you can measure each one of those thin lines and stuff, those sharp line spectra, pretty readily. Neon actually has more lines even than mercury, which is kind of cool. Now again, the hydrogen bulb looks kind of purplish, and here's hydrogen in this example. Here's a helium bulb, and neon's right there. And again, you can see the different wavelengths and stuff. We'll talk about what this means, emission spectrum, here in a little bit. These are all emission spectrum, which is different than an absorbance spectrum. In astronomy, this is critical because when you have a star, say many, many light years away, there's no way that you can go next to it, take a sample, come back to your lab and measure what's inside it. That's not going to happen. So what people do is they take these spectrographs, which is basically measuring the spectrum, and they see some very complicated kind of procedures. But if you dig through that enough, you can then figure out, hey, there's hydrogen and hey, there's mercury or whatever. So they can actually tell the composition of stars and exoplanets, stuff like that, through these spectrographs. Making it more difficult for astronomers, though, is something called the Doppler effect. And this is something in physics you'll talk about more. Doppler effect makes the wavelength shift. If you've ever been at a train station and a train goes by fast, it goes, all right, sound effects not necessary, sorry, but the train is only giving out like one sound, but the sound seems to change as it moves by you. This is the Doppler effect. And there are red and blue shifts, so you can see the little lines down there on the spectrum. They're moving back to the left and the right as the objects move around. So it's pretty crazy. But again, astronomers are able to tackle all of this and figure out how this works. And again, my hat's off to them. That's pretty cool. Astronomy is awesome, but the electric pickle, I would argue, is even cooler. So remembering that if you excite an atom with electricity, like the light bulbs we saw earlier, you'll begin to see light from it. And if you take a pickle, of all things, and you basically shove electricity through it, that's a variac that the person is controlling, and it's connected to basically a series of wires, you can actually see the sodium ions in the pickle light up, and it makes that kind of glowing thing. And I have seen this with my own eyes. A student a few years ago was really fascinated by this. So he brought in pickles. He made this work. He actually had some pickles that were soaking in some potassium ions, like fake salt potassium, and it made kind of a purple thing. But anyway, after a while, the pickles begin to smell, so I warn you in advance. But anyway, it is pretty cool. Now, in the electric pickle, it's the sodium ions, which are exciting. If you've ever seen a fire, like at a campfire, the campfire is usually yellow. The yellow is a color very indicative of sodium ions. And so that glow, that yellow glow you see is from the sodium ions in the pickles used as preservatives and stuff like that. So it's pretty cool. But like I said, my student replaced the sodium chloride with a potassium chloride, basically fake salt, let it soak for a while, and you can actually change that color. So my student with the potassium chloride, he made kind of a purple glow in the pickle, and that was pretty neat. Let's say that you have barium, and barium, if you excite it, makes kind of a green flame. So what color would you think you'd see in an electric pickle soaked in barium chloride? Well, again, it has nothing to do with the pickle. It's about what it's soaked in. So the sodium was yellow, potassium was red. You can probably imagine that barium then would give a green flame. And I've heard of this being done. I haven't actually done it before, but I think it would be cool. I've never seen a pure black flame, but I do, of course, like Lord of the Rings a lot, so probably it's something I've seen before. But anyway, in real world science, probably not going to happen. Kind of cool. So all of these, again, besides just being darky cool, are example of these sharp line spectra and how they bring out colors from certain elements.